Hi, and welcome to another lesson regarding the topic of base 2. This time we are going to learn about signed numbers. Objectives of this lesson. You will recall the traditional ways to represent negative numbers, mostly in the decimal case. You will learn how to invoke subtraction by addition in base 10. You will learn about the 2's complement method to negate a binary number. Motivation, or why would you want to know this? We want to be able to represent negative numbers inside the computer, or maybe just to tell the processor about negative numbers. We want the usual arithmetic to work with the new representation for negative numbers. That means we want the usual plus operator that the processor knows how to invoke to work with the new representation, to work in a smooth way with the new representation. Let's look at the traditional way of negating numbers in the decimal case. In base 10, we traditionally use the minus symbol to represent a negative number. Some examples: minus 345, for example, or minus 7. These are two examples of negative numbers. They just mean the lack of 345 units, or the lack of 7 units. You must be familiar with the idea of minus number. That is something that you usually learn in elementary school. We can invoke arithmetic operations between positive numbers and negative numbers. For example, we can try to solve this one. Minus 5 plus 7, all in base 10, equals actually 7 minus 5, which equals 2. Another example would be minus 11 minus 32. That would actually equal 32 minus 11, because twice the minus becomes a plus, and we get eventually 21 in base 10. And it seems like everything works just right in the old way, so why would we want to try something new? Well, I think you should consider a new way to do it, and we are going to present it here. The drawbacks of the traditional minus. Before adding any two numbers, we have to check their signs and then act accordingly. That means we can't just do or invoke the operation we want to do. We have to check some things before we do it. For example, if one of the numbers is positive, like in this example, and the other one is negative, then we have to invoke subtraction. If one of the numbers is negative and the other is positive, then we have to invoke subtraction in the other way. If both of the numbers are negative, then actually the work we are going to do is an addition. Only after the addition is done, we are going to do the subtraction. And also there is the usual case of just a usual addition, if both of the numbers are positive. According to the signs of the numbers, when we are going to do a plus operation, we have to check the signs and then decide if we are actually going to do an addition operation or a subtraction operation. Another point is this: the usual subtraction is hard to invoke. And that is because we have to handle borrows from far away bits. Maybe you remember this from the last exercises when you had to invoke subtraction between two numbers. Maybe you are used to the decimal case, but in the binary case it can get pretty weird because you have to borrow from very far away bits and do it one by one. It's not nice like adding numbers where the carry is very simple. We would be very happy, at least I will be very happy, if I only have to use the addition operator, because I really like it. I like the addition operator, but the subtraction operator is not very nice to invoke. Example of how this could be done is this. If I want to calculate a minus b, then I will calculate a plus minus b instead. Well, minus b will be some magical representation of b that will conform and give me the wanted result in the end. Another drawback is that we have to keep the minus sign before any signed number. That means keeping one extra symbol before every number. And mostly when we are dealing with the processor and assembly language and the usual computers we have, we don't have an extra symbol. We only have 0 and 1. We don't have three symbols like 0, 1 and minus. That might form a problem. So we are going to try to do something a bit different. We are going to try to subtract by addition. Let's look at some example. We want to solve the following. 932 in base 10 minus 151 in base 10. How could we solve this? And I mean, how could we solve it in a bit different way? Not the usual one, where you just put them vertically on a paper and try to solve it. We are going to try to solve it using only addition. The first thing we do is some kind of a trick. We add and remove 1000. Why 1000? Because both of these numbers have 3 decimal digits. So we are going to add this number, which has exactly 3 zeros, 1000. And we are going to see what's the point of this in the close future. This is how it is going to look like. We add it here, the number 1000. And again, we don't forget to subtract it here in the end, to make sure that the final result is not going to be something different. We give ourselves the right to put the 1000 exactly here, next to the 151 number. Then we just want to solve this part. The rest we are going to deal with later. This is indeed a subtraction operation, however, it is a pretty easy one. Maybe we can even say a mechanical operation, because subtracting a number from 1000 should be pretty easy. How can we usually do it? We just take every digit and complement it to 9. For example, this one, 1, is going to turn into 8. Then the next one, 5, is going to turn into 4, because 9 minus 5 is 4. And then the last one is a bit different, because we have to actually make it 1000 and not 999. Then we also add 1 in the end. We are going to see it more rigorously in a moment. So we have this result, the one in purple, and we are going to replace it in the original equation here. We are going to replace this part inside the braces with 849. And we get this. We get that 932 minus 151 equals just like before, but we replace the braces with the purple result. And now we get something new to solve. Here we have an addition, which should be mostly easy because we like to do addition operations. At least I like to do them. They are easier for me than doing subtraction. And finally we will have to subtract 1000, but we are going to deal with this later. First we add these two numbers, and this is the first part where we actually do real work. This is the real work in this calculation. We add these two numbers. We will have to do it vertically the old way, and we get this number as a result, 1781. And subtracting 1000 again is going to be a mechanical operation. We just remove the 1 in the end. And this is pretty magical. So instead of subtracting those two numbers, which could be pretty hard, we just turn this equation, or maybe exercise you could call it, into two mechanical subtraction operations and one real addition operation. The first mechanical subtraction operation is here, 1000 minus 151, which is very easy to do. And the second one is this one, 1781 minus 1000, This is also pretty easy to do. You can just look at it and know the answer. And the real work is here, where we add those two numbers that you can see here. So eventually we conclude that the result is 781 in base 10. And it really seems that we only used addition to solve it. The rest of it was just mostly mechanical. So we saw that 932 in base 10 minus 151 in base 10 equals 781 in base 10. We also saw that adding those two numbers, if you remember, we obtained this number 849 from the original number 151 by subtracting from 1000. We can see the similarity here, that the only difference is this one. And this is very interesting. This is an interesting phenomenon. We actually got subtraction by addition. Instead of trying to solve this, which is pretty hard, we changed it into trying to solve this addition problem. And the addition problem is easier. We just had this one digit in the end that we had to remember to remove. What actually is the relation between 151 in base 10 and 849 in base 10? Well, this is the relation. That is how we got this number. The subtraction from 1000. This operation of the subtraction is mostly mechanical. Every digit d is replaced by 9 minus d. And finally, we add 1 to the result. Why is that? Because if we just replace every digit by 9 minus d, we get a complement to the number 999, not to the number 1000. In order to get a complement to 1000, we have to add 1 to the final result. 849 is virtually the negation of 151 in the world of 3 decimal digits. We call this method of turning 151 into 849 the tens complement. Let's look at a summary of this method. We want to solve this problem, this subtraction problem. First, we confine ourselves to the world of 3 decimal digits. We could choose something else, but 2 decimal digits is not going to be a good choice here because we have numbers that are too large. We could also choose, for example, 5 or 8 or even 32, but it might be too much here. 3 is about the minimal number of decimal digits that we can choose. First, we find the tens complement of the second number, of the number 291. We do it by finding 9 minus d for every digit d, and finally adding 1. So it looks like this. First, we convert every digit to its complement. 2 is going to be 7, 9 is going to be 0, and 1 is going to be 8. You can check that the sum of every 2 digits here is 9. 2 plus 7 is 9. 9 plus 0 is 9. And 1 plus 8 is 9. And eventually we add 1 to make sure that it is complement of 1000. And we get this number, which is the complement of 291 in base 10. Finally, we add those two numbers and we get a result, which is about too large. We have this first digit 1 that we will have to remove. We consider only the lowest 3 digits. That is because we confined ourselves in the beginning to the world of only 3 decimal digits. We have to be consistent with our choice. If we would have chosen something else like 4 digits, then in this step we would have to consider 4 lowest decimal digits and not only 3. This is very important. Finally, we get that the result of the subtraction is going to be 346, just like here. And again, we managed to solve a subtraction problem using only addition and some mechanical operations.